Hello everyone, my name is Siyuan Xu. Today I'm presenting my work, Online Distributed Price-Based Control of DR Resources with Competitive Guarantees. This is a joint work with Li Renyu, Xiaojun Lin at Purdue and Jin Dong and Yaoshuo Xue at Oak Ridge National Lab. Demand response is considered crucial for future smart grids. When there is significant penetration of renewable generation, the utility can invoke the flexibility of the demand, which can shape system peak and benefit system reliability. Buildings' HVAC systems are important sources of demand flexibility, which we will focus on in this paper. Existing technique on residential demand response can be classified into two categories: direct load control (DLC) and price-based control. With DLC, utility directly manipulates the consumption of the load. However, DLC is usually considered too intrusive to buildings. Price-based approaches assume that utility can only send price incentive signals. This form of control is therefore more favorable when customers wish to retain the autonomy and privacy. However, it is difficult to attain performance guarantee if buildings are completely free in response to their price. So it remains an open question for the utility using price-based control to attain performance guarantee, especially when there is significant uncertainty in future inputs. To solve this open question, we propose a framework for utility to perform price-based control with competitive performance guarantee in terms of controlling system peak. Our solution has two key ideas. First, we introduce the notion of flexibility contract, which specifies how much flexibility a building has, and the reserve price when the building promises to invoke its flexibility. This gives utility a guaranteed level of demand flexibility, which is important for utility to attain the performance guarantee. But note that reserve price is only meant to be used sparingly. Second, we designed a distributed algorithm for computing the price incentive to smoothly transition between the non-reserve price and reserve price, all in the presence of future uncertainty. So our main contribution of this paper is to guarantee a provable low competitive ratio (CR) under a certain amount of future and load renewable uncertainty. Let me now present the system model. Again, the HVAC part of building offers significant flexibility. However, we do not want the utility to directly control or observe the building HVAC system. Instead, we use a flexibility contract. A key component of flexibility contract is the virtual battery, which is defined here. So here the UT denotes the energy charge or discharge to the virtual battery. The variable XT denotes the state of charge SOC of VB. The variable A denotes the dissipation rate of VB. There are additional parameters associated with VB. Delta denotes the VB energy capacity, and minus denotes the discharging power limit, and plus denotes the charging power limit, which we assume to infinities. In addition, our proposed contract includes a pair of reserve price, P high and P low. Wherever the price signal given by the utility is P high for discharging or P low for charging, building has to take any given charging or discharging signals. Now we are about to present the model related to price-based control. We assume that time is loaded and indexed by T, which range from 1 to capital T. We consider a single utility company serving n building with demand flexibilities. The utility can send a fixed price incentive plus a variable incentive lambda Ti to buildings. Note that when price is within this reserve price range, building is free to choose their own response, ETR, decided by a payoff function known only to buildings but not to the utilities. Its response ETI can be measured by utilities. Also, building has to declare its real-time baseload consumption, which falls within the prediction range given day ahead. If we subtract the BTI from ETI, we get a signal to UTI. Each building's current SOC can be updated by this value. Lastly, if the price hits the reserve price, the utility will instruct the building with the target response. Further, the utility also serves other load and has renewable generation. For simplicity, we subtract the renewable energy from the non-building load at each time t, and denote it by phi-t. Since renewable generation has significant uncertainty, we model this by an uncertainty set, which was also given day ahead. A bit of summarize here. So at day ahead, the utility is given the uncertainty y, which consists of prediction range of base load and uncontrollable load. At time t, only base load and uncontrollable load known at or before time t is revealed, so we denote that as ZT. At end of time horizon capital T, all revealed demand is known, and we refer that as a realization Z. The goal of the utility is to utilize the flexibility of the building to reduce the peak drawn from the grid. The peak EP pi simply is the maximization of capital ET over the entire time horizon, where the total consumption ET is simply the summation of all buildings' consumption plus the uncontrollable load. Now let us define the comparator ratio of an online algorithm. For an online algorithm, at each time t, it will decide its energy consumption, capital ET, based on the information that has been revealed at time t or before time t. At the contrary, offline solution refers to one knows at the entire future in advance, and the solution of which we denote as E star of z. Then, the comparator ratio of an online algorithm, pi, is the maximum ratio between an online peak and offline optimal under all possible realization. Our goal is to achieve a provably low comparator ratio given the uncertainty set y. Now that we have presented the system model, we can move on to our solution. Our proposed solution will be developed in 3 steps. First step is to develop direct VB control, which is about obtaining the optimal comparator ratio, assuming the utility can directly charge or discharge each VB. Then, we try to achieve price-based control, which is about using only price signals to reach the same decision as the direct VB control. Lastly, a robustification procedure is applied to attain an online algorithm with both the optimal comparator ratio and good average case performance. In the first step, we assume that direct VB control, that is, the utility can directly manipulate the consumption of the load. Our goal is to design an online algorithm with a provable comparator ratio. However, existing methods cannot work with multiple VB. Therefore, we define an aggregate VB as the work by Hall et al. The main guarantee is that any feasible charging or discharging decision to the aggregate VB can be split into feasible decision into individual VBs, which is okay for direct VB control set. So for the direct load control, we adopt EPS algorithm. EPS stands for estimated peak scaling. We take a method similar to this reference here and change it to work for our setting. The idea of EPS algorithm is as follows. assuming that we know the optimal competitor ratio is eta y star. At each time t, we first compute the estimated peak based on lowest possible demand in the future. Then the consumption ET at time t is set to be this value, which is eta y star times the peak estimation. If this decision overcharged VB, we will lower the ET so that the VB is full. So it only remains to determine eta y star, so that it needs to be set such that the VB will never be over-discharged. Now we are going to talk about how to find the optimal competitor ratio. The intuition is as follows. Starting with a full battery at time t1, we need to ensure by following EPS decision, the VB at a later time t2 is always above minus C, which means they will never be over-discharged. Then we can derive this expression here. By rearranging this expression, we obtain a low bound on the eta y star. By maximizing the right-hand side over all possible realization and all possible T1 and T2 pair, we can derive the best lower bound on eta y star. We then prove this lower bound is exactly the correct eta y star. Our main contribution of this part is to handle the dissipation. In step 2, we want to convert Dirac VB control to price-based control. Goal is to use price signal so that the building's own decision add to the same value under Dirac VB control. This is non-trivial, however, because when buildings decide to charge or discharge in their own ways, they may deplete the flexibility in the system. The following is example. Suppose we have two buildings. The maximum charge each VB can hold is 5, and the discharging power limit is 3. There is no dissipation involved. The utility can aggregate these two VBs into a single one with capacity of 9 and discharging limit of 4. Suppose at time slot 1 to 3, the utility wants to discharge 3 to 4. The utility can simply split the discharging decision evenly between these two VBs. For example, minus 1.5 here means both VB are discharged 1.5. The third row shows that both VB's state of charge are within their capacity limit. But if buildings are allowed to make their own decision, they may choose the decision in the fourth row. Specifically, in time slot 1 and 2, only building 1 discharges VB. The SOC are shown in the fifth row here. Now at a later time slot 3, when the utility wants to discharge another 4, there is no longer a feasible solution. Building 1 is already full, cannot take any further discharge, while building 2 can discharge 3 because its discharging limit. So a sequence of aggregate decisions that was feasible under Dirac VB control is no longer feasible when buildings choose their own decisions. To overcome this difficulty, we introduce a new sufficient condition that eliminates the mentioned infeasibility problem for the future. Our condition will ensure if the building's decision satisfies these 4 conditions, then for any sequence of future aggregate decisions supported by the aggregate VB, there always exist buildings' individual decisions that respect individuals' VB limits and also add up to the designed value. Specifically, let beta I in the constraint can be thought of as the fraction of future aggregate decisions sent to building. Assume such a constant splitting. The first constraint ensures that the individual VB discharging limit is respected. The second constraint ensures the decision of individual buildings always add up to the target decisions. The final constraint ensures the individual VB capacity limit is respected. Based on the sufficient condition, we can then formulate a centralized optimization problem PC. Here, the objective is the payoff of all buildings minus the cost of energy minus a special term that captures the deviation of beta I from beta I0. In the constraint, the first constraint ensures the building's decision add up to the same desired value as Dirac VB control. The second constraint and the third constraint ensures buildings' VB capacity and power limits are met. The last four constraints are the new sufficient condition, ensures there always exists such feasible solution. From this centralized formulation, we can now derive a distributed solution. We use standard duality theory. Note that only the first constraint and the last constraint are coupling building's decision, so we introduce lambda and mu I respectively for these two constraints and follow standard duality theory to decompose this centralized algorithm into a distributed solution. From just defining the centralized problem, we can now derive a distributed solutions. In each iteration, utility sends a tentative price signal to the buildings. After feedback from building, utility updates its price signals and sends again to the buildings. This process repeats until either algorithm converges or a max number of iterations has been reached. Note that this distributed algorithm is easy to implement and incurs low communication overhead. The algorithm mentioned will work if all buildings respond adequately to the price signals. However, since we allow the buildings to make their own decisions, it may occur some buildings may not respond adequately. Reserve price now kick in. Specifically, when utility updates the price of each building in distributed algorithm, some buildings will typically hit the reserve price earlier than others. Once they reach the reserve price, the utility can directly calculate its energy consumption, the value of which is shown here. Accordingly, buildings have to charge or discharge the amount of energy specified. One issue with EPS is, although it achieves the optimal competitive ratio for the worst-case inputs, its average case performance can be very poor. So we use the standard robustification procedure introduced in this work. The robustified algorithm ensures the optimal competitive ratio as well as a reasonable average case performance. We use both synthetic and realistic traits to test our algorithm. For synthetic ones, suppose there are 4 buildings, and one of them is responsive in the sense they are sticking to their baseload consumption. This figure shows a scenario where peak occurs near the end of time horizons. Here, x-axis denotes the time slot, y-axis denotes the energy consumptions. Uncertainty set is shown by these 2 green dashed lines here. The actualization is all those blue dots. For comparison, we use MPC as benchmark. This curve is the MPC under Dirac VB control. Note at the beginning of the MPC decision is very high. This is because MPC used the middle point of future uncertainty as the prediction and minimized future peak. It then only executes the aggregate consumption decision for the current time slot. That is why its decision at the first time slot is very high. In contrast, Robustified EPS, which shown by this purple cross, it is very low, because it takes the lowest possible future peak as the estimate. If the future realization remains the lower bound, then EPS would have attained a much lower peak than MPC. Now let's take a different scenario happened at a later time slot, 21. The demand suddenly increases. Both EPS and MPC DVBC increase the consumption in the same way, facing the sudden peak. For a price-based control version, however, Robustified EPS is still fine, following the same decision as direct VB control. However, MPC with price-based control cannot reduce the peak as much. The reason is that MPC price do not have a new sufficient condition that we introduced earlier. Therefore, it cannot retain the same aggregate flexibility in the system when one of the buildings becomes unresponsive. For simulation with realistic traits from Melia, we consider 20 buildings that participate in our demand response program. Assuming that 25 of buildings are misbehaving and all legends are similar to the last eye, we can observe that the peak of our robustified algorithm is much lower than the peak of MPC. A summary of our work: we use VB model to define the amount of flexibility that building can offer. Our main contribution is to provide a distributed online algorithm that can attain competitive performance guarantee in terms of reducing the system peak and the future uncertainty. Further, with the robustification procedure, our solution can not only attain the optimal competitive ratio, but also do well for the average case inputs. For future work, an interesting question is how to incorporate the charging limits of VB. Further, we also plan to conduct larger-scale simulation studies to verify the scalability of our algorithm. That's all for our presentation, and thank you all for listening. I'd like to answer any questions or is there any comments.